Welcome to this presentation, Channeling Energy to Ecosystems and Sequestering Atmospheric CO2, Seeing Plankton with New Eyes. My name's Bob Brewin. I'm a lecturer based at the University of Exeter in the UK, and I put this presentation together with a colleague, Giorgio Dall'Olmo, based at Plymouth Marine Laboratory in the UK and the National Centre for Earth Observation. So I'm going to begin this story by talking about phytoplankton. These are microscopic single-celled algae that live in our oceans. They're an important component of the Earth's system. They're at the interface between light and life in the ocean, channeling solar energy into the marine ecosystem, helping propagate that energy up the marine food web, through zooplankton to fish, and even to humans through the seafood we eat. Phytoplankton also photosynthesize, so they convert inorganic carbon in the form of CO2 into organic carbon. And by doing this, modulate the atmospheric CO2 concentrations. In fact, if phytoplankton were removed from the ocean, its estimated atmospheric CO2 concentrations would be 50% higher than they are today. Hence, they're an important component of the Earth's carbon cycle. Now, if we look at biomass of phytoplankton, and we were just to take a snapshot of what the biomass is of phytoplankton in the ocean, it's actually tiny in comparison to the biomass of terrestrial plants on land. About 0.2% of the biomass of terrestrial plants on land. However, phytoplankton are among the most dynamic primary producers on our planet. They have life cycles in the order of days and to weeks, whereas terrestrial plants have life cycles in the order of years to decades. And as a result, the primary production, so this conversion of inorganic carbon in the form of CO2 into organic carbon, which can be stored, is equivalent to that of primary production by terrestrial plants on land, thought to be around 50 gigatons of carbon per year. And hence they're a very important component of the Earth's carbon cycle. Okay, so they produce this 50 gigatons of carbon in the surface layer. Now around 40 gigatons of that carbon is converted back from organic carbon into inorganic carbon, so back into CO2, through the processes of remineralization within the euphotic zone. But around 10 gigatons of that carbon gets transferred down into the ocean interior, where it continues to attenuate, with around 2 gigatons thought to reach the bottom of the ocean surface and around 0.2 gigaton being buried into the sediments per year. So this flux of organic carbon from the surface down into depth is known as the ocean biological carbon pump. And it's this process that forms this gradient in CO2 that we see on the left here. And if we were to switch this pump off, this CO2 gradient would equilibrate, and hence a lot of carbon dioxide would be released back into the atmosphere. Okay, so this 50 gigatons of primary production in the surface layer, we have an uncertainty around that number. It's thought to be in the region of around 40 to 60 gigatons of carbon per year, depending on the approach we take to estimate it. And that uncertainty increases as we move down through the water column. So the uncertainty in the export production is around 4 to 12 gigatons of carbon per year. So we have a higher fractional uncertainty in a way on that number of 10 gigatons of carbon per year. And it's worth noting that these uncertainties are high. So in the order of 6 to 10 gigatons of carbon per year, which are much higher than the annual ocean sink of CO2. So we have large fluxes in primary production, export production, and we have large uncertainties in these fluxes. And in order to improve our understanding of the ocean carbon cycle and for understanding carbon budget verification, we need new observations like a global ocean array of biogeochemical algae floats that we can use to understand better these fluxes and reduce these uncertainties. Now I'm going to start with ocean primary production. And before I start talking about biogeochemical algae floats, I'm going to go back 40 to 50 years in time and look at another transformative technology that changed our understanding of the ocean carbon cycle. And that's satellite remote sensing of ocean colour. So for those of you who may not know much about this technology, cameras in a way on satellites take pictures of the ocean in the visible region of the electromagnetic spectrum, so the same region we see with our eyes. And by analysing spectral variations in that colour or that light reflected from the ocean surface, we can look at ocean phytoplankton. We can get robust estimates of the chlorophyll A pigment in phytoplankton, which is a measure of its biomass and important in the process of photosynthesis. So these satellites, one of the first satellites launched by NASA, the Coastal Zone Colour Scanner, really transformed our understanding. And to sort of put it into perspective, satellite remote sensing of ocean colour was considered among the biggest achievements in biological oceanography in the 20th century. So this was alongside the discovery of chemiosynthetic organisms on hydrothermal vents in the ocean. So just to put it in perspective how important this transformative technology has been. And we're now approaching a period where we have nearly 25 years of continuous ocean colour observations going from 1997 to present. And we have managed to view the ocean's phytoplankton in a way we never imagined before. We can see the spatial dynamics of phytoplankton, how they change seasonally in the high latitude regions, and we can look at interannual variations in phytoplankton at an incredible resolution. Ocean colour remote sensing also allowed us for the first time to produce robust global estimates of ocean primary production. And this is just a map from one of the first studies that did this by Alan Longhurst back in 1995, who estimated that global ocean primary production is around 50 gigatons of carbon per year and equivalent to the primary production by plants on land. However, notwithstanding the incredible temporal and spatial sampling of satellite remote sensing, there are some disadvantages to satellite remote sensing. One of the first disadvantages is that the signal is only representative of the surface layer, so around 20 meters in depth. Now, over the majority of the world's oceans, there exists a forest of phytoplankton hidden from the eyes of the satellite that can be seen with a biogeochemical Argo float. Another disadvantage is that passive ocean colour remote sensing requires light to observe. So we can only observe the ocean during the day, and we can't observe it at high latitudes in winter where the sun is very low in the sky. Again, a biogeochemical Argo float is not limited by this ambient light. Satellites also can't see through clouds. Biogeochemical Argo floats are not limited by clouds. So there's a huge potential to combine the two observational systems to improve our understanding of ocean primary production. And I'm just going to illustrate simply how we can do that here. So our primary production, which is denoted by P in the grey box here, can be estimated with good accuracy with using three variables here: the chlorophyll A concentration, a measure of phytoplankton biomass, the amount of light availability, and this relationship between photosynthesis and light, known as denoted here as PCHL. Now, from satellite, we can see the surface chlorophyll, and we can also see it vertically with the ocean biogeochemical Argo flow. We can see the surface light fields from satellite. And we can also see how the light changes vertically using a biogeochemical Argo flow. And we can measure the backscattering coefficient from satellite. And we can also measure backscattering vertically using an ocean biogeochemical Argo flow. Now, this backscattering information, together with the chlorophyll and the light, can help provide information about this relationship between photosynthesis and light. And we also have a suite of other variables we measure on a biogeochemical Argo flow, nutrients, oxygen and pH, that can help improve our estimates of ocean primary production. By combining these biogeochemical Argo flow, a global biogeochemical Argo flow array with satellite observations, we can produce 3- and 4-dimensional fields of primary production. This is just an example of that of the backscattering coefficient by a paper by Hervé Klostre. Synergistically integrating these two observational platforms will reduce uncertainties in ocean primary production. Okay, so moving on to how carbon is then transferred out of the euphotic zone into depth, so this export production term. Well, it's worth just reviewing how that works. So how does organic carbon transfer from the surface to depth? Well, first it can transfer simply by gravitational sinking. So this is the sinking out of the water column by dead phytoplankton, by aggregated organic material, by fecal pellets. So this is fecal pellets from zooplankton. It can also be transferred by physical transport means, and it can also be transferred by the vertical migration of zooplankton. So just to mention this last process a bit, what happens is the organic carbon produced by the phytoplankton, some of it gets eaten by the zooplankton. They then migrate down into the deep waters where they release some of this carbon at depth. Now together, these three processes are thought to control the total export of organic carbon. Okay, so we can use biogeochemical Argo floats to look at this total export term by simply tracking the stocks of, in this case, particulate carbon in time and with depth, as illustrated here by a paper by Dell'Olmo et al. In 2014. We can also look at total export by tracking changes in the oxygen, pH and nitrate in the water, which can help us inform us about total export production. So biogeochemical Argo floats can really help us understand this flux of total export. We can also look at the physical transport term. So not only total export, we can begin to understand individually how these three pathways influence the export processes. Now, one physical transport means that's thought to be important is a process known as eddy subduction. So this is the sort of eddies, three-dimensional eddies spinning in the ocean, transferring carbon out of the surface ocean down into depth. And we can track these signatures using an ocean biogeochemical Argo flow. We can also track a process known as the mixed layer carbon pump. So at the surface of the ocean, there's this mixed layer, this layer of turbulence at the surface of the ocean that changes. It can be deep, it can be shallow. And fluctuations in that change in mixed layer depth can transfer carbon out of the surface ocean down into depth. So biogeochemical Argo floats can track how physical processes transfer this organic carbon to depth. We can also get an idea of the gravitational sinking of large aggregates. And we do that by monitoring the spikes in optical signatures from our backscattering and our chlorophyll sensors, as illustrated in some of these papers here. And we can also begin to understand the processes of vertical migration of zooplankton using ocean biogeochemical Argo floats. Again, a nice example from a paper recently published here where they looked at spikes down in the mesopelagic region of the ocean where the zooplankton are known to exist, and shown how these spikes can be related to zooplankton abundance. And there are also new sensors that have been integrated on these ocean biogeochemical algae floats that can take images of large particles like zooplankton and have the potential to improve our understanding of this part of the total export puzzle. Now, there's no doubt a global array of biogeochemical algae floats will transform our understanding of the ocean carbon cycle. And we know that simply for the fact that the few biogeochemical algae floats we have put into the ocean have already transformed our understanding. They've been used to understand the seasonal cycles of phytoplankton under the sea ice in high latitudes, for example. They've observed unexpected blooms of phytoplankton in winter months in the North Atlantic. We've seen how hydrothermal vents can trigger phytoplankton blooms in the Southern Ocean. And we've quantified important processes in the attenuation of carbon with depth, such as particle fragmentation using ocean biogeochemical algae floats. And we've even understood how hurricanes impact ocean productivity using biogeochemical algae floats. Now, many of the processes that control this flux of carbon, organic carbon, out of the ocean down into depth, as illustrated here, are temperature dependent. And we know our ocean temperatures have been rising, and that this increase in temperature is disproportionately focused in the surface regions of the ocean. We need new observational platforms like a global ocean biogeochemical array to improve our understanding of these processes and also to monitor them in the face of increasing environmental change. Thank you for listening.